Hello and welcome to MT3. We are still on Green's functions, and in this lecture we're going to look at examples. Now I have explained the theory behind Green's functions and the Dirac delta function in previous recordings. This time we're just going to look at examples, and some of these are in Riley, Hobson and Benz 15.2.5 and also in Arfken, Weber and Harris chapter 10. Let's have a reminder first as to what is it that we're trying to do. So we've got the linear operator L operating on Y, and it's a differential operator which has taken this special form, and this form has been chosen so that L is Hermitian. Now for exactly why this is a form which makes L Hermitian, we'll have a look at Arfken's book or Riley's book, but we've also looked at it in a quiz in a previous lecture. Alright, so L operates on Y to give you f of x, which is the source function, and generally this equation will be valid in some range a to b. It could be in an infinite range or semi-infinite range. Now the way we solve this is using the method of Green's functions, which says we find g of x and t such that L, and I put an x there, it's the same operator, but the x indicates that the operator operates on the x coordinate only. So L of x operates on g to give us the Dirac delta function, delta of x minus t, and we define g subject to the same boundary conditions we had for the equation here. And if we do that, then the solution y of x is given as the integral transform from a to b of g of x comma t f of t. So f, this is the source function which is f of x here it becomes f of t. It's convoluted with the g, the Green's function, integrated over the t coordinate, and you get the solution y of x. Alright, and how did we do this? We did this by taking our range a to b, splitting it into, choosing a point t which is between a and b, could be anywhere between a and b. We define it, we then have region 1 which is defined to exclude t with a little t minus epsilon, so an epsilon neighborhood around t, we exclude t. So we have region 1 where t is excluded, we have region 2 where t is excluded, this time from x values larger than t. And that lets us define g, the Green's function, in a piecewise way, where we have a function a of t times y1 of x, b of t, y2 of x, where y1 and y2 are solutions to the homogeneous equation L of y is 0. Why the homogeneous equation? Because we argued that if you exclude the point x, is equal to t from here, then effectively this Dirac delta is 0, because you don't have the point x is equal to t included in there. So we have the homogeneous equation L operates on g to give you 0. Okay, that's not moving very well, is it? And then in the other part so this is valid, this upper portion of this piecewise definition is g minus, and this is where x is less than t but greater than the left hand boundary, and then we have g plus defined in an analogous way with different functions c and d, which are functions of t, and here x is greater than t but less than or equal to the right hand boundary b. Alright, we have 4 unknowns a, b, c, d, so we need 4 conditions to solve, and those 4 conditions are as follows. 2 of them are boundary conditions. The third is a continuity condition, which says that g plus when x is equal to t must be equal to g minus when x is equal to t. This was imposed, and this is valid only if you're dealing with a second or higher order ODE. And then we have a fourth condition, which is a discontinuity condition, which says that the derivative of g plus with respect to x at the point x is equal to t minus the derivative of g minus with respect to x at the point where x is equal to t, this is equal to 1 over p of t, where p is the function in our linear operator. Right, and then the solution could be written in this way. We have y of x is equal to the integral from a to x. We're integrating over t, by the way, and in this range we use g plus, and then we continue the integration from x to b, so it's the entire range we are integrating over. But in the left hand range we use g plus, and in the right hand range we've got g minus. Okay, the reason is here t is less than x and here t is greater than x. Right, so let's put this machinery to work now, and I'm going to solve this particular problem. It's solved in either Riley's book or Arfkin's book, I can't remember. I'm going to solve it systematically and slowly so that you get an idea of how this is working. So we have our differential equation, y double prime is equal to f of x. F is a source function, we don't know what it is as yet. And we have boundary conditions, y of 0 is 0 and y of 1 is 0. So the differential equation needs to be solved in the range 0 to 1. Okay, so we are solving it in this range. And our goal is to find g of x and t, and hence find y of x in terms of the source function f of x. That's what we want to do. We want to solve it for y of x. Step 0, and I strongly recommend you do this each time you approach a problem like this. Draw a line, the x-axis, put down the end points of the applicable to this differential equation from 0 to 1 in this case. There's a point t in between these two limits, and that defines a region on the left hand side and the region on the right hand side of t. On the left hand side of t we have g minus, and that's the Green's function we're going to define. On the right hand side of t we've got g plus, and then we have two boundary conditions, one applicable on the left hand side, so y naught is equal to 0, y of 0 is 0, and on the right hand side we have y of 1 is 0. Yeah. Now one of the reasons for doing this, as you'll see, is that when you draw something like this, you can see right now that this boundary condition, the left hand one, will be applicable to g minus, and the right hand boundary condition will be applicable to g plus. Okay, that's one of the reasons why I strongly advocate drawing this. So step 1 is to find the solutions of the homogeneous differential equation. The homogeneous equation is the one where the source function is 0, so we have just a simple equation, y double prime is equal to 0. Solutions are 1 and x, they are linearly independent. So y1 of x is 1 and y2 of x is x. Step 2, write down the Green's function in this range. Remember, this is the range in which we are integrating the differential equation from 0 to 1. So the Green's function is defined in this two-part way, a times y1 plus b times y2, where y1 and y2 are functions of x, and a, b, c, d are functions of t. The first part is equal to g minus, that's where x is less than t, but greater than or equal to 0. And the second part is equal to g plus, that's where x is greater than t, but less than or equal to 1. Just a reminder, a, b, c, d are all functions of t, and y1 and y2 are functions of x. Step 3. Use the boundary conditions on g of x comma t. Now, I talked about using the boundary conditions in the introduction, but this is the first time you're going to see how it is done. So we're going to regard g of x comma t as a function of x. Now, the way I like to think about it is to regard t as a parameter here. It's fixed, so you can write this equivalently as as a function g as g subscript t, where t is our parameter, fixed parameter, and that's a function of x. Now this satisfies the same boundary conditions as y of x. So as we had y of 0 is 0, so we're going to have gt of 0 is 0, and we had y of 1 is 0, so we have gt of 1 is 0. Or equivalently, in the original form, g of where x is 0, but t is of course just some constant there, that is 0. And then g of 1, where x is 1, t is anything, that's equal to 0. So this boundary condition is valid where x is 0. Now that's on the left hand side. So this is going to apply to g minus, as I mentioned above. Yeah. So the left hand boundary condition is applicable to g minus, and the right hand boundary condition is applicable to g plus. And this is important. You have to decide a priori which of the boundary conditions are applicable to which parts of g. So here, I've just said this, the boundary condition at x is equal to 1 is applicable to g plus. So g minus of 0 comma t is 0. What this means is a times 1 y1 of 0 plus b times y2 of 0 is 0. Remember, y1 is 1 and y2 is x. So what this gives us is that a plus b times 0 is 0, or a is 0. The second boundary condition on the right hand side is applicable to g plus. It says that g plus evaluated at x is equal to 1, any value of t, that's 0, which means c times y1 of 1 plus d times y2 of 1 is 0, or c times 1 plus d times 1 is 0, or c is equal to minus d, or as I've used it, d is equal to minus c. You can put this into the Green's function, and that gives you a Green's function now with only two unknown constants. G, the Green's function, is equal to b times x. Remember, b is a function of t in general. B times x, where x is less than t but greater than or equal to 0, and it's c times 1 minus x. This condition gives you the 1 minus x, where x is greater than t but less than or equal to 1. So now we have two unknowns, b and c, both are in principal functions of t. Just a note here, this definition of g satisfies the boundary conditions at x is equal to 0 and x is equal to 1. And this just is a reminder again that g depends not only on the structure of the linear operator L, but also on the boundary conditions. Now, and this is and we're going to see an example here. That means if you change the boundary conditions, you're going to change g. Okay, this is what's going to happen. All right, now the continuity condition. It says that g plus evaluated when x is equal to t and any value of t, that's equal to g minus when x is t and t could be any value. So just a reminder again, this could be written as x is t and x is t. Okay, so that first coordinate is the x coordinate. If you apply it to our Green's function given here, what we're going to have then is g plus is this part here. So let's put that as a reminder again. This is g plus and this part here is g minus. Then we've got g plus evaluated when x is equal to t. In fact, it's this one here, my apologies. So c of, let's write this down properly. That it doesn't make any difference, but it's good to get things in the right order. Right, so we have c of 1 minus t is equal to b times t, and this is g minus. Okay, so that's one condition, call it, I've labeled it as 1, and then we have the discontinuity condition, which states that the derivative of g plus evaluated at x is equal to t minus the derivative of g minus at x is equal to t is equal to 1 over p of t. Now here p of x is 1. I put a how there. If you go back to the differential equation we were given, it was simply y double prime is equal to f of x. Now if you go to how p and q are defined, here's p and there's q. So in our case q is 0 and p has to be 1, so that we just get a second derivative of y over here. Okay, so p is 1, so we get minus c minus a is 1, or c is equal to 1 minus a. That's our second condition. Solve for g of x and comma t, and from 1 and 2 what you can show quite easily is that a is equal to t minus 1 and c is equal to minus t. Therefore you can write the entire Green's function now. G of x comma t is equal to t minus 1 times x, that's g minus, and that's valid when x is less than t. And then we have in the part where x is greater than t, it's t times x minus 1, and that's g plus. It's a piecewise function. Is it continuous? Well, when x is equal to t, you will have t minus 1 times t and t times t minus 1. So it's continuous. But if you differentiate with respect to x, you will find that the slope is not continuous. Okay, and now we can write down the solution. So the solution is given as y of x is equal to the integral from 0 to 1. Those are the range of applicability of this solution. And we have the Green's function times the source function, and note the change in the variable. It's not f of x, it's f of t now, because we're going to integrate over t. We split this range into two parts, from 0 to x, and this is where we have g plus, and then from x to 1, this is where we have g minus. Now you put in g plus. What is g plus? It's given by t times x minus 1. The x minus 1 can be pulled out of the integral sign because you're integrating over t and not x, but the t remains there. So we have the integral from 0 to x of t times f of t dt. And likewise for g minus, you pull out an x, and we have the integral from x to 1 of t minus 1 times f of x, f of t dt. Now once, if you tell me what f is, we can put the function f in there and we get the solution out. It's that simple. So, you know, if you wish, you could now try a few functions of f and see what you get, and make sure that the solution you get is the same as what you would have expected from the standard ways of solving this differential equation. So I've got a few things for you to think about and seriously think about, work through. What does g look like for a fixed t? If you plotted it, what would it look like? What would g look like for a fixed x? If you're good at using Python for making two-dimensional plots, plot the function g of x and t as a function of both variables. What does it look like? It's kind of nice to see these things. And then the third question is, find the derivative of g with respect to x and plot it for a fixed t. What does that look like? Is there indeed a discontinuity at the point x is equal to t? Please do this. I mean, it's always nice to get some insight into what you're up to. Another example here. So now we've looked at an ODE of the form given here, which you don't always have differential equations in this form. So let's have a look at the ones which you might be more familiar with. And this is actually an exercise for you. So here L, the linear operator L, is given by the second derivative with respect to x plus capital P of x. It's not the same as the little p of x from the first equation, times d by dx plus capital Q of x. And that's defined to be your linear operator L. And the x here, again, subscript x indicates that this operator operates on the x coordinate only. So the Green's function again satisfies the standard relation. We assume that function p is continuous in a to b, and q has at the most finite discontinuities in a to b. And assuming that g is continuous in a to b, show that the derivative discontinuity condition is now given like this. So we don't have a 1 over p of t, we just have a 1. Yeah, so that's the difference now. I'd like you to try this out. The solution to this is in either Riley's book or Rifkin's book, but you should be able to do it using the techniques which I have described in the introduction to Green's functions. That is the previous lecture. Okay, you can pause for a break at this point, because now we're going to look at another couple of examples. And here we're going to see that the Green's function depends on the boundary conditions. So we'll have a look at this differential equation, y double prime plus y is f of x. So our linear operator is the second derivative with respect to x plus 1. And if you compare this equation, this linear operator with the one given above, what we've got is q is 1, p is 0. All right. So that's, I mean, I just made this comparison, but you don't need to, we won't need this. Right, so we're going to solve this in two cases. The first case is we're going to choose our range from 0 to pi over 2, and our boundary conditions are the endpoint or homogeneous boundary conditions, where y is 0 at 0 and y is 0 at pi over 2. So y is 0 on both the boundaries. And the second case we're going to solve this for is where this is what's called an initial value condition, where both conditions apply to the left-hand boundary. So y is 0 at 0 and y prime is 0 at 0. Okay, so in this particular case, we're going to solve the equation from 0 to infinity. Yeah, we could just as well have made it a right-hand side boundary where we could solve it from minus infinity to 0. But we're going to do it from 0 to infinity. This is called an initial value condition. We could have it just as well as a final value condition. Now they are quite different. These boundary conditions are quite different, but they have one thing in common. Both of them keep this linear operator Hermitian. Yeah, and once again, the reason why this is an important thing will be apparent when you look at more advanced treatments of Green's functions. But this is not described in either Riley's book or Narfkin's book. Okay, so our goal is to find the Green's function for both cases A and B. So let's have a look at case A. Alright, so these are our boundary conditions here. We've got to solve the homogeneous equation. It's y double prime plus y is 0, and this is an equation you've seen a million times before. The solutions are the sine and cosine of x, and they are linearly independent. So we can now write down our Green's function as a times sine x plus b times cos x in the region where x is less than t but greater than 0, and it's c times sine x plus d times cos x in the region where x is greater than t but less than or equal to pi over 2. The first one is g minus, this is g minus, and the second one gives us g plus. We apply our boundary conditions. At the point x is equal to 0, g of 0 comma t is 0. This applies to g minus because it's on the left hand boundary, so we apply to this thing here. That's the one which accesses the left hand boundary. And then we have a condition on the right hand boundary. When x is pi over 2, g of pi over 2 comma t is 0. This is accessible to this side. That means we apply to g plus. So we get a times sine 0 plus b times cos 0 is 0, or b is 0. And likewise here we have c times sine of pi over 2 plus d times cosine of pi over 2 is 0, which means c is 0. So our Green's function is now greatly simplified. It's now a times cosine of x on the left hand side and d times sine of x on the right hand side. Then we apply the continuity condition, like g plus when x is t is equal to g minus when x is t for any value of t, and that gives us d of sine t is equal to a of cosine t, condition 1. Then the discontinuity condition. This is the new form which I've asked you to prove above here. We're using this form because our differential equation is of this form. All right. So here we are. So this gives us our condition 2. Solve them to show that a is sine of t and d is cosine of t. And that gives us our Green's function. The Green's function is given by sine t cos x when x is less than t, and cos t times sine x when x is greater than t. All right. Now, I'm not going to go any further. Once you have your source function, you can use this Green's function to solve for the solution y of x. But let's instead go on to the next boundary condition, the B case, where we have the initial value conditions that y of 0 is 0 and y prime of 0 is 0. And now we are solving in the range 0 to infinity. So as before, because we have the same homogeneous equation as before, the Green's function is in this form. But now let's apply the boundary conditions. So both boundary conditions apply at the point x is 0. It's 0 here and 0 here. That means both boundary conditions are at this point here, which then apply to the g minus solution. There's no boundary condition for g plus. So g minus of 0 comma t is 0. This, by the way, means b is 0. And derivative of g minus at x is 0 is 0, which means a is 0. Please verify that these two are indeed the solutions. What this means is our Green's function is written as 0 if x is less than t and x is greater than or equal to 0, and it's equal to c times sine x plus d times cos x when x is greater than t. Yeah, so we've completely eliminated the left hand part of the Green's function. It's 0. Now we apply the continuity condition, that g plus of t comma where x is t is equal to g minus where x is t, and that means we have a condition on c and d. That's the first condition. The discontinuity condition gives us an analogous condition on c and d. You can solve them, it's quite easy, to find that c is a function of t, which is cos of t, and d is minus sine t. You can put it together, so your Green's function now is 0 on the left hand side when x is less than t but greater than or equal to 0, and it's equal to this thing, which is just sine of x minus t when x is greater than t. This is quite a different Green's function given, if you compare it to the one we had earlier. Here. Look at this Green's function. It's the same differential equation, different boundary conditions, and the Green's function has changed completely. So it definitely does depend on the boundary conditions. Now there's a link between the Green's function and the Wronskian. Yeah, so if we're not looking at a very particular kind of Green's function. So by the way, if you were feeling that that was too much, you can take another pause here before going on to this part. We're nearly at the end. Otherwise, you can continue. So here we are, the Green's function and the Wronskian. Now, let's have a look at our range of integration from a to b, and we have a boundary condition at a and a boundary condition at b. All right, so this is not an initial value condition, this is the homogeneous condition where we have a condition on a and b. And I've chosen them to be y of a is 0 and y of b is 0. Okay, now, so we have our linear operator L operates on y to give you f. F is our source function. And now we consider the case when the homogeneous equation, so this is this one, where the source function is 0, and it has solutions y1 and y2 as before. But these solutions are special because y1 is chosen to satisfy the left-hand boundary condition. So y1 of a is 0. And y2 is chosen to satisfy the right-hand boundary condition. So y2 of b is 0. It's important, by the way, that y1 does not satisfy both boundary conditions, and nor does y2. Otherwise, things go completely wrong if that happens. Okay, in this case, the Green's function is written in terms of y1 when x is for x in the left hand side. This is where the point A is accessed, and it's got a y2 on the other part where we have the point B, which can be accessed. Now I have a question here. Why must this be the case? I'd like you to answer this yourself. Why do we have to choose it in this form? Why couldn't we choose it the other way around, or why couldn't we choose a linear combination? I'd like you to show that the only possible solution is that we have y1 on the left hand side and y2 on the right hand side. And of course we have some unknown functions of t, a of t and b of t, which multiply these two. So check that G satisfies both boundary conditions. Now to determine a and b, we use the continuity condition, which says that G on the right hand side when x is equal to t must be equal to G on the left hand side when x is equal to t. That gives us this condition here, and then the discontinuity condition, which gives us this condition here. Okay, now please verify these two also. The solutions are quite trivial. You get a is given by y2 at t divided by w of t, and b is y1 of t divided by w of t, where w is the Wronskian. And just to remind you, the Wronskian is defined as y1 y2 prime minus y2 y1 prime. And if you forgot what the Wronskian is, it's I described the Wronskian in a previous lecture on differential equations. And this lets us then write the Green's function in terms of the Wronskian. So we have a y1 of x times y2 of t divided by the Wronskian at t, and y2 of x times the y1 of t divided by the Wronskian at t. Sorry, not x, this is t. Right? Now, the full proof for this case, I believe, is in Arfkin's book, or Riley's book, I can't remember which one, but you should be able to prove it without their help. And this form is sometimes useful, so I would expect you to be able to work with this form when needed. Okay, so that's where I'd like to stop with our examples of Green's functions. You'll find more examples in both the books. Please have a look at these, and of course you will see them in our exercise classes. Thanks for watching.